All right, let's just do a little bit of review for the final, okay? All right, so the final is Wednesday from 1 to 3, and it's in North Santiam Hall, right? So, yeah, 110. It's not here, it's in a different room. The reason for that is all the construction noise, and at least they say there's going to be a lot, so I didn't want to have it in here. All right, so that's the first floor of North Santiam Hall, which is that newer building as you're walking in from the north parking lot. Okay. All right, now I'm just looking at the review. Does everybody have a copy of the review? Okay. So first thing we got is, why don't we just kind of walk through. Now, there will be some pump curve stuff on this final, so look at the pump curve questions that are in chapter 14. That is something that you'd want to do, all right? So let's kind of have a look here at some things that to be going over and to understand. The first thing is centrifugal pump theory, which we're not getting too deeply into that, but the idea is that the water comes in to the spinning impeller, and the impeller throws the water out towards the edge of the volute, and then it works its way around the volute. The volute is designed so that it gets bigger. There's a bigger opening as you work your way around the edge of it. What that does is it slows the water down. So you have energy in the water on account of the impeller in the form of velocity head, but what happens is that energy gets converted into pressure because you're basically forcing the water to slow down. That's what's happening, okay? So that's basically how a centrifugal pump works. It's putting that energy into the water, it converts into pressure, and then it flows from there with pressure, okay? Now, it's pressure, usually if you look at a gauge on a pump, it's in PSI. Of course, we measure that type of pressure in feet of head. That's how we measure it, okay? Okay. All right. So, if you're ever rebuilding a pump, you remember that what an impeller does is throw the water outwards. You don't want it cupping the water, as you would see over there on the right. You want it throwing the water outwards. Okay. All right. All right. From there, we pretty much go into one other kind of little topic, and that is pumps in series and parallel. Okay. Parallel pumps double the flow for the same pressure. Okay. Series pumps have the same flow, but they double the pressure. Okay. That's the difference. It's on page 134. So pumps in parallel might be what's called a duplex lift station, where you have two pumps that can come on if necessary to drain a wet well. Series pumps I think of as being like a multi-stage pump. All right. Now, the next thing we did was a combination of a few different things, and that's TDH, total dynamic head. Now, what that is, I think it's important to kind of keep the forest and the trees separate in your mind. The forest is you're adding two things. You're adding the lift, how high you're lifting the water, but then to that you're adding the head loss. Okay, so you add those two things together. Head loss, or sometimes it's called friction loss. Okay, and this is the total energy that the pump needs to move the water from one reservoir to another. You have to lift the water, but you also have to overcome the head loss in the piping system. So when you find the TDH, the total dynamic head, you're adding those two things up, is what you're doing. So the first thing you do is just find the elevation difference in the reservoirs. The other thing I'll mention on TDH is there's a formula for it, okay? So, if you're taking this test, and, I'm sure you'll have to find a TDH, just look at that formula. You see total static head. That's the lift of the water. Just figure that out. You can get that from the elevations on the reservoirs. Right here was 36 feet for for this one. All right. But then you also have to find the head loss. And that's a little bit more involved. So the process there is to find the length of the pipe and then find the equivalent length of the fittings by taking the L over D value off of the chart, multiplying it by the pump diameter in feet. Okay. Adding those up, you get the total equivalent length of the fittings. So basically, in this example here, I'm on page 139, when you push the water through the piping system, you got to push it through 186 feet of pipe, but you also have to push it through the fittings. And the fittings have the same head loss as 118.6 feet of pipe. Okay? Because those equivalent lengths of the elbows, the ordinary outlet, and the ordinary inlet add up to 118.6. So when you add those together, the pump, from the pump's point of view, it's like it's pushing it through 304.6 feet of pipe. So you can find the head loss for that, and then add that to the lift of the water, and that gets you the TDH, total dynamic head. Okay. So that's the total energy this pump will have to develop. Okay. So that's called total dynamic head, TDH. And what you're doing there is you're just finding the lift of the water plus the head loss. That's what you're doing. All right, so are we good on that? Okay. We're good. Okay, now once you have that number, what you can then do is figure out the horsepower. That's the next thing. It could be on the test, and this will be on the test, I'm sure. And again, there's a formula. The horsepower is gallons per minute times the head divided by a conversion factor of 3960. It's in the lower right-hand corner of the formula sheet. Okay. So what this is, the head is the TDH. The flow is in gallons per minute, okay? So you're going to take however many gallons per minute you got, multiply it by the TDH, and then divide it by 3960, and that's the horsepower that is delivered to the water, okay? So you can think of that as being water horsepower. All right. Now, that's what you have to deliver to the water, but you need a pump and a motor to do that with, and they're not perfectly efficient, okay? So there's an example of finding horsepower, just gallons per minute times the TDH divided by 3960. That's all you got to do. Okay. Now, you got to do a little bit more, though, to figure out your system, because if you have a certain water horsepower, you have to look at the efficiency of the pump and the motor. You have to divide the water horsepower by those efficiencies, and that gets you back to what's called the motor horsepower. That's the horsepower that comes into the motor. Okay? So we all right with that? You divide by both efficiencies, because the horsepower that comes into the motor is bigger than the horsepower that actually ends up being delivered to the water. Each step of the way you lose a bit of power because the motor and the pump aren't perfectly efficient. So you have that drop in power. Okay, so I always try and remember which one's going to be bigger. Okay, the further back you are in the system, the bigger the horsepower. So the motor horsepower is going to be bigger than the brake horsepower, which will be bigger than the water horsepower, because you've got all these efficiency losses. So what I would do then would be to take the water horsepower and divide it by both efficiencies, and that'll get me the motor horsepower. Okay. And then once I've got that, I can convert that into kilowatts, which is what the power company uses. And then I could figure out things like costs. See, what I could do, I could figure out how many hours a day I'm running, because the power company charges you for kilowatt hours, power times the time over which it's delivered. Okay, and then if you know the cost per kilowatt hour, you can figure out how much it costs to run the pump. So those are the two big sets of calculations I think you'd be doing, is the TDH and then the efficiency stuff to get kilowatt hours, okay, and the horsepower equation. All right. Now there is a little bit more stuff here that we have to look at, and that's the pump curve stuff, which we were looking at last time. And there's 3 homework problems. You don't have to turn them in, but I would have a look at these so you're comfortable reading pump curves. All right, so let's say we've got a TDH of 30 feet and a 7.5-inch impeller for this first one. You know, the basic way you read that is you find your TDH. Let's say this is a single stage pump. So this pump curve is in your book. That's 152? Mm-hmm. Okay, thank you, 152. So if you've got a TDH of 30, you just come on over until you hit the pump curve that you're dealing with. 7.5 inches, that's the second one from the top. Once you hit that, you just read straight down and you can get the flow. Now, if you're given the flow, you can read up and intersect over and go to the left and get the TDH, okay? Either way. So I think I went a little too far over there. It's about 350 gallons per minute. Everybody might get a slightly different answer. We don't get too worked up over an exact answer on this because they're just full pump curves. Okay. Then you have these bands going through that represent efficiencies. So we're right about here. It looks to me like I'm a little bit inside of that 80% line. I would call that 81%, I guess, if I had to call it something. Now remember this little thing up here. The less bowls you have, the less efficient you are. So the bowls is the stages of the pump. How many impellers or volutes, whatever you want to call them, are in there. Yeah, we've got 1, so we subtract 4 from this and get 77%. So that pump would be about 77% efficient. You might get something a little different than I am. That's fine. Okay. And then read up till you hit a horsepower line and take it over to the right. And that looks to be about 3.2, and that's a brake horsepower. The reason they give you brake horsepower is that's how you size the motor that you would put on this pump. Okay. So do we have any questions on that one? Okay. Now the next one there, are you guys okay with it? The next one is a 2-stage pump. Okay, that means 2 bowls. and the TDH on this one is 50. Okay? Right. And you're right, 50 isn't on the chart, and that's a tip-off what's going on here, because if you remember with pumps in series, they develop twice the head. So this chart is set up for one bowl. Yeah, you divide it by 2 and get to 25. When you get to 25 now, you come on out here, and I think it's a 7.5 inch impeller. Yeah, it is. So hit that second line down and then read down. And I called it about 435. I mean, again, it's not like I have the perfect number here. It looked to me to be a little bit more than 425, so I just called it 435 gallons per minute. You might get something a little different. It's no big deal. Okay, so that is the flow, because pumps in series don't change the flow. Okay, it's the same flow going from one bowl to the next. Okay, but the thing that will change, it's going to affect a couple of things. The first thing is the horsepower. Okay, we're up right around here, and I don't know what I called it, about 80%. It might be a little different. I mean, I don't know. If you just show your math on this, we're fine, because if we've got 2 bowls, the efficiency drops by 2. So 80 minus 2 is 78%. Okay, so you got to remember on this pump curve, the number of bowls you have, which is also the number of stages, they mean the same thing, affects the efficiency.
And the fact that we already divided it by 2 to get to the 25 won't affect.
Not the efficiency.
Okay.
Yeah, it won't. Okay. But it will affect the power. Because what this pump curve represents is one bowl. Okay, so when you do the power here, you're going to intersect the second curve down and read to the right. And again, that's kind of a tough one to read. I got 3.5 is what I got. But again, you might get something different. But the important thing here is what you do with that, because that's per bowl. But this is a 2-stage pump. There's 2 bowls. So this is going to require about 7 horsepower, twice 3.5. Okay? Because what you're doing, see, if you kind of go back to that basic horsepower equation, it's flow, which hasn't changed, times head, which has. See, because there's 2 bowls. This is only for 1. You're going to have twice the head on this pump. So as a result, you're going to have twice the power requirements. So that's what's going on with that.
So for the total head, we would divide it by like 2 to have a single pump, and then when you get to the horsepower, that's when you multiply it back by 2 to get.
Yeah, right, yeah. So yeah, you take the head you're given for a 2-stage pump, you divide it by 2, but then you got to double the horsepower after you figure the stuff out off of the chart. Okay. Okay. All right. And then the last one there, I have an old copy of the book on 14.9. What does it say? Does it say 500 gallons per minute or 350? 500.
With the 8.5 inch.
Okay, so 8.5 inch, 500 gallons per minute. So you're going to come here at 500. All right, and then you just read up till you hit the 8.5 inch. And you can see those impeller sizes there on the left. And, you can see what's going on with this pump curve. It works for 5 different impellers. Yeah, okay. So you can, let's see, so 500 gallons per minute. We want to find the TDH, 49. Okay. Yeah, okay, so 49 feet, that's the pressure, that's what the pump's going to have to, will be outputting for head. Okay, now we can start looking at the other things here too. I put the efficiency right around 60% from reading those efficiency lines. I'm just reading this one right here. 60%. Okay. Now, this is kind of fun. This is different than the other one in how it does horsepower. See what they're doing, they're running bands through here for different horsepowers, okay? So what we've got, because they're just rating the horsepowers on available motors, I think is what they're doing. 10 horsepower runs through there, and then 15 horsepower is next. We're just a little bit above the 10, so I'd say this requires 11 brake horsepower. But it looks to me like with the motors available, you know, they're telling you what the available motors are with those bands. So I think we're at about 11 brake horsepower there. And then the last thing with this is the NPSH, right about there. It looks like you need about 15 feet of available NPSH, okay? So if you're using this pump in a lift situation, which I assume it's made to do, you're gonna need 15 feet of NPSH. That's to be the energy of the water when it gets to the balloon. Yeah.
I have a question. So from the beginning, I got the rest of it was fine, but how'd you get you say 80% or 8.5?
8.5 for?
I think it was TDH. So you went from the 500.
Came over. I got about 49.
Oh, okay.
Over here.
Okay. That's why I was.
Okay, yeah, I didn't, I'm sorry, I didn't run that line over. There we go. There. So it's about 49, 48,
Okay.
somewhere. Okay. All right, so that's the deal with this.
So will the motor size be the same as the BHP?
Well, yeah, the required brake horsepower for this is 11. Given the information that I'm seeing here, it looks like you would not go down on motor size. You'd have to go up. So the next one up would be to go to the 15 horse motor, even though it'd only be we're putting out the 11, you know, to run the pump.
Because that's just the motor sizes that they give you here.
Yeah,
So, okay.
and I'm assuming those are the available motors they've got for this pump. Okay. So that's the stuff that could be on the, at least the most recent stuff that could be on the test. I'm going to put a couple other things on here too, but is that a good start there? Are we good on the pump curves? All right. So you definitely, you want to know those kind of theoretical things that I just was going over. You also want to know about these calculations, all right? And the calculations are the TDH and then the horsepower type stuff, okay? Now there's a couple older things on here, but there's just two of them, but I want to be sure that you know about these. The first one is a flow problem, something like that. This is off the second midterm. So be sure that you can do one of these. Hang on, I'll be right back. All right, so on this one, we just want to know the flow rate in a pipe. So what we're doing here is we're using this basic equation right there, Q equals VA. Okay, So to get the flow rate, you need the velocity, which you're given, and then you need the area of the pipe. Now that's a circular pipe. Pipes are circles, so what the area is pi r squared. And that's, on the formula sheet, if you need that. I think I give you the value of pi also. Yeah, pi is 3.14, okay? So if you need the area of a pipe, you take pi times the radius squared. Now the one thing on this though is that pipes are usually called out in inches. We usually want to know the area in square feet. So we want the radius in inches, and then we want to convert that into feet by dividing it by 12, okay? So a 9-inch pipe has a 4.5-inch radius, which is 0.375 feet. So you take pi times 0.375 squared, and you get 0.442 square feet. Okay. And then you multiply it by the velocity. So that's a basic flow problem there. And that gets you cubic feet per second. So you take the area of the pipe times the velocity of the flow. So we got any questions on that? All right. Now the other thing we're going to do is force is pressure times area, which actually can be pretty similar to this. You got to find, you're going to take two things and multiply them together to get the force. So let's see here. Well, we have a look at that here in just a second. Right, so here's an example of that off the first midterm. What you want to do in this case is find the pressure on the middle of the window. So you're given 12 feet to the top of the window, but you want to go down to the middle, which is 2 more feet. So that's 14 feet down from the water surface. Okay, so that's how you would start that. You want to come down from the water surface to the middle of the window, 14 feet, and then multiply that by the pressure per foot. So that's going to get you 6.06 pounds per square inch. So even though you've got a depth in feet, the conversion factor gets you into pounds per square inch. Okay. And then what you want to do is multiply that by the area of the window. So here we have a round window. This is kind of the opposite of what we just did because we've got the diameter of the window in feet. You want to take half of that, which would be 2 feet, to multiply it by 12, and that's 24 inches. So the area of that window would be pi times 24 inches quantity squared there, and that'll get you the area in square inches. That matches the pounds per square inch pressure you've got. So you take the pressure in pounds per square inch, multiply it by the area of the window in square inches, and you come up with the force. Okay? So that's a couple of other things that you could do on this to you know, that will be on the final. The Q equals VA for the flow rate, and then the F equals PA for the force. Okay. So you want to be able to do these things too. So do we have questions on that? All right, so that's kind of a run through what to be doing for the final. So that's in North Santiam Hall 110. It's Wednesday from 1 to 3. So a different room. Okay.